Talked about several ways that we can prove that two triangles are congruent. We started by looking at congruent triangles and the definition of congruent triangles, which says that in congruent triangles, all three sides and all three angles have a corresponding part in a second triangle that is congruent. So from that, we came up with some more congruence theorems that we could use for other cases. So today we're going to look at, once we know that triangles are congruent, what can we use that for? So let's start with these two triangles. So these two triangles are congruent, and we want to know how they are congruent. So if we look at these two triangles, there's two sets of congruent sides and one set of congruent angles. And based on the placement, we have side, angle, side. So we know that they're congruent by side, angle, side. And let's come up with a congruent statement for the placement of the vertices. So let's start with the first one, and we have some freedom in naming the first one. Let's just go with alphabetical order, A, B, C. So when I name my second triangle, I need to go with its corresponding parts. So this angle is marked, and it's vertex A. So in the other triangle, the marked angle is D. So we're going to have to start with D. Then, after that, we went up the side that was marked with one line. So from D, we go to E. And then our third one, we traveled from B to C, so that's going to be E to F. So triangle ABC is congruent to triangle DEF by side, angle, side. Now, let's look at what else we can figure out. So after we look at these markings, we already know that AB is congruent to DE, that angle A is congruent to angle D, and that AC is congruent to DF. So once we know that they're congruent, there's a few other pieces that we can say. So since they're congruent, that means that all three sides and all three angles have congruent parts. So let's start with our last side. So once we know that they're congruent, we know that side BC will be congruent to EF, even though it wasn't marked previously. We also know that angle B will be congruent to angle E, since they're both at the base of this one marking side. So angle B is congruent to angle E. And finally, we know that angle C is congruent to angle F. So the reason we can make these assumptions are from the definition of congruent triangles. To help us out, we have another way that we can say it if we need it in a proof. So if we need to use this in a proof, we are going to use CPCTC. And what CPCTC stands for is corresponding parts of congruent triangles are congruent. So the important thing here is that the triangles already have to be congruent. Once we know that they're congruent, we know that all those other parts are going to work out too. So let's look at a proof in which we will need CPCTC. So we're starting out with segment HJ is parallel to LK. So HJ is parallel to HJ to LK. And also JK is parallel to HL. So we have two different sets of parallel sides. So this is our given. Whenever we're talking in triangles and we're saying that segments are parallel, the most likely suspect for the angle pair that we're going to be using is alternate interior angles. So alternate interior angles are those angles that are inside of a Z. So let's start with this first set. So if I'm looking at this set of parallel lines, here's the Z, and those angles within are going to be here and here. So if I want to name these, I need to name them H, J, L, and J, L, K. So that's our first set of alternate interior angles. So now we have those. Now let's look for another set. So the other Z is going to be here. So even though it's backwards, it still works as a Z. So for our second pair of congruent sides, we have this angle and this angle, the two angles that are contained in those corners of the Z. So for these, we can name these angle HLJ, and then its congruent angle will be KJL. And that's by the alternate interior angle theorem. So whenever you're using the Z, you're going to use alternate interior angle. So now we have two angles within each triangle. So we're looking at the top triangle and we have these two, and then in the bottom triangle we have these two. So we still need something else. In order to use two angles, we need a side. So to find a side that's congruent, let's look at what we have. So since we have a shared segment within, that's always going to be congruent to itself. So if we need a side, let's look for that one that's shared. So this segment right here in the middle is shared. It's in both triangles. So for reflexive property, that's going to be LJ is congruent to LJ. So it's congruent to itself. Now I've set myself up for angle, side, angle. So since I have those three parts, I have angle, side, angle. And let's look at how we can name the triangles. So we can just start with any of the triangles, start with a vertex in the first one. So say we want to go HJL. So in the second triangle, we need to find the corresponding part to H. So this corresponding part, it's an unmarked angle. That's going to be angle K. So this will be triangle K. And then J had one marking, so its corresponding part is L. And finally, we go to J. That's the two marking angle. So once we have two triangles that are congruent, we can use this new theorem, CPCTC, to say that all the other segments are congruent. So since HJ and LK are corresponding parts in congruent triangles, they're also congruent. So our reason here is CPCTC. Corresponding parts of congruent triangles are congruent. Let's look at another proof. All right, so this proof has 7 steps. We're starting out with another parallel statement. So whenever we have that parallel statement, let's look at where those lines are. So MS is parallel to TR. So we have these two lines. Let's look at the Z between those. And notice that with these parallel lines, we have a forward Z and a backward Z. So let's start with blue. So let's look at this Z first. So if I look at this Z, I'm going to find those angles contained. And since these angles only have one name, like this M only goes with this angle, I can name it by one name. So since angle M and angle T are within the Z, those are congruent. And if we go the other way, so let's look at the other way of the Z. Those contained angles are S and R. So we also know that angle S is congruent to angle R. All right, so I skipped my first step. My first reason is given. My second reason, since I used the Z's, that's alternate interior angle theorem. All right, so now we have this next statement, which is MS is congruent to TR. That was one of our givens. So let's get us another color and mark that. MS is congruent to TR. So since MS is congruent to TR by given, I notice that I have two angles and a side. And based on how they're placed, it's angle, side, angle. So once I have enough information, I can prove that the triangles are congruent. And from there, I'm going to look at my triangle names. So starting with this one, let's say we do MSA. So So if I name this one MSA, then I'm going to go with those corresponding pieces. So one marking, so my first will be T. My second will be the 2 marking, so that's R. And then my final will be no marking, so that is A. So now I have enough information to use CPCTC. So since I want to use CPCTC here, let's go on and look at what we have. So these are already marked, so we have 2 sides that we can say are congruent to other parts, and we have a set of angles that we can say are congruent. We're working towards saying that something is the midpoint, so let's think about what the definition of midpoint is. If we need the definition of midpoint, then we can say that the definition of midpoint is that it cuts it into 2 congruent sides. So to cut it into 2 congruent sides, that means that those 2 pieces need to be congruent. Luckily, those are things that we can get from CPCTC. So MA is a corresponding side to AT. So we can say that MA is congruent to AT. And that's by CPCTC. All right, and so now that we have this, we're already down to where we can prove it, so we don't actually need this 6th step. So we know that this, the 2 congruent pieces, is the definition of midpoint, so we can prove that A is the midpoint by that definition. Okay, we have one more proof to go through. So on this last proof, we have this figure right here. So we have these triangles in the middle, and then we have triangles coming off the side. So the first thing that we're given is that QT is the perpendicular bisector of US. So perpendicular bisector has 2 pieces. It's perpendicular and it's a bisector. So let's start with the perpendicular part. So if things are perpendicular, that means that it meets at least one right angle. So since we have QT to US, we can go on and say that both of these are right angles. So angle, and there's multiple angles there, so we have to name it by all 3. QTU is a right angle, and angle QTS is also. So angle QTU and angle QTS are right angles. That is the definition of perpendicular. So now that we have that these are right angles, let's go on and finish this part off. Since they are right angles, that means that all right angles are congruent. So angle QTU is congruent to angle QTS. That is the right angle congruence theorem. All right, so now we've finished off and we've got a set of congruent angles. Let's look at what we can get from bisector and decide if we're going to need or that these are right triangles or not. So if we need hypotenuse leg, we're going to need that these are right triangles, but we don't have to do that just yet. So next, let's look at what a bisector is. So the bisector part, a bisector cuts something into 2 congruent pieces. So if we're talking about it being a perpendicular bisector of US, then this piece and this piece will be congruent. So our next thing that we can say is that UT is congruent to TS. All right, so that is the definition of bisector. From there, notice that we have one side and one angle, so we still need something else. So let's go on and pull in something that we already know. So notice that they share a side. So since they share a side, we can use the reflexive property. So I can say that QT is congruent to itself. And that will help me prove that those triangles are congruent. So QT is congruent to QT by the reflexive property. So now I have enough information about these triangles that I can say that the two triangles are congruent. So to make that congruent statement, I need to name the first one. And let's just go with QTU. And then name accordingly. So QTU is going to be congruent to QTS. And the reason I can say that is because I have side, angle, side. I didn't need hypotenuse, leg. All right, so now I've set myself up. I have two congruent triangles. That means that I'm ready to say that other parts are congruent if I need them. So looking at this triangle over here, so this triangle on the side, the only piece that's in the other triangle is QU, and with this one, we have QS. So we're prepared to use those congruent triangles to say that. So next statement, QU is congruent to QS. And that's going to be by CPCTC. Corresponding parts of congruent triangles are congruent. So I've worked my way out of the triangle. We can stick with this for a minute. Now we're up to 3 markings. So now I have this side. I am kind of out of things that I can do with these congruent triangles, so let's go on and bring in those other givens. So to introduce the other givens, let's bring in green. So now we have that QV is congruent to QR. So QV, 4 markings, QR, 4 markings, and VQU is congruent to RQS. So by introducing those givens, we're set up to prove that these triangles are congruent, which is what this should say. So what we were trying to do is to prove these two triangles. So I can't remember exactly how it says in the notes. It should say something like triangle VQU is congruent to triangle RQS. And now we have enough information to do that as well. So let's go on and prove that. VQU congruent to RQS. And our reason here, in this triangle on the outside, we have side, angle, side. Since that's what we were trying to prove, we didn't need the 10th step. So we're finished after 9. Please let me know if you have any questions from this section.